Hi everyone, this is lecture 24 and we're starting chapter 9. Chapter 8 on random vectors we're going to skip because we don't need it. This chapter is about sums of random variables like w equals x1 plus x2 plus dot 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 plus xn. In earlier chapters, we spent a lot of time studying the case of n equals 2 when w is equal to x1 plus x2. Now we're going to generalize these ideas to n random variables. Our goal is to understand the properties of a sum of n random variables. We'll start by looking at expected values, then we'll go on to variances, and then we'll look at distributions. At various points in this course, we've looked at a random variable w, which is the sum of two random variables. Here we'll call those two x1 and x2, although in other places we call them x and y. And we learned that the expected value of the sum is equal to the sum of the expected values. Our first theorem in this chapter generalizes this result to n random variables. In this case, the expected value of the sum is equal to the sum of the expected values, just as we saw for n equals 2. This generalization is really a consequence of the original result for n equals 2. To see what I mean, consider w3, which is equal to x1 plus x2 plus x3. But we know also that w2 is equal to x1 plus x2, so in fact w3 is equal to w2 plus x3. And now w3 we have written as the sum of two random variables, so we know that its expected value is the expected value of w2 plus the expected value of x3. And since w2 is the sum of x1 plus x2, we know that this equals expected value of x1 plus expected value of x2 plus expected value of x3. So this is our claim for n equals 3. For arbitrary n, the next slide uses the same idea in a proof by induction. More important than the proof, we need to keep in mind that this theorem, it's true for all x1 through xn. It doesn't matter if they're independent or dependent. For any collection of random variables, the expected value of the sum is always the sum of the expected values. Now that we've found the expected value of a sum, the next thing we want to know is the variance. You already know that for n equals 2, the variance of w2 is equal to, it's the variance, of course, of x1 plus x2, and that equals the variance of x1 plus the variance of x2 plus 2 times the covariance of x1 and x2. This theorem generalizes that result to n random variables. In the generalization, we still have the sum of the variances, but now we have 2 times the covariance of each pair xi and xj. Another point to keep in mind is that this double summation is a little bit tricky to evaluate. For instance, in the case of n equal to 3, we have that the variance of w3 is equal to the sum of I equals 1 to 3, variance of xi, plus 2 times the sum I equals 1 to 2, plus and then the sum of j equals I plus 1 to 3, covariance xi, xj. So this is equal to, variance x1 plus variance x2 plus variance x3, and now we have plus 2 times the double summation. And if you're unfamiliar with these double summations, you first think about the sums for I equals 1, and for those you have j equals 2 to 3 covariance x1 xj, and then you think about I equals 2, and when I equals 2, j goes from 2 plus 1, which is 3 to 3 covariance x2 xj, and then you see that this becomes covariance x1 x2 plus covariance x1 x3 plus covariance x2 x3. And now what we see is that maybe this double sum is a little more clear. It's the sum of the three variance terms plus 2 times the sum of each covariance term for each pair of random variables. Covariance x1, x2, covariance x1, x3, covariance x2, x3. Once again, this claim is also true for all collections of random variables x1 through xn, and the reason is because the dependency structure between the random variables only shows up in terms of the pairwise covariances. The proof of this is pretty short, but it's short because it has condensed a few steps. We write the variance as the expected value of wn minus its expected value, and then to make the algebra a little simpler, we use mu I to note each expected value of xi. And since the wn's are the sum of the x's, the mu w, the expected value of w, is the sum of the mu i's. That was our previous theorem. Putting these pieces together, we have that the variance of wn is equal to the expected value of wn, which is summation I equals 1 to n xi, minus the expected value of w, which is summation I equals 1 to n mu I, and we have to square that to get and take the expected value to get the variance. And now we do one more trick, which is we rearrange the inner sum to be a single summation. And now from here we have that this expected value is the quantity up here. Now we're ready to look at the final two steps in which we take this summation squared and write it as the same sum twice in a row. Here is the sum once with dummy index I, and here is the same sum again, and that's the sum over on the left side squared. And now when we bring out both summations, this one and this one, and write them here and here, we get the expected value of xi minus mu I, xj minus mu j, which is just the covariance. And then finally, there's one last step where we take this double sum and we take out all of the pairs where I equals j. Because when I equals j, the covariance of xi, xj is just the variance. The most important special case of this theorem is when the xi's are uncorrelated. Remember that there's this confusing bit of terminology that xi and xj uncorrelated. That means that covariance xi xj equals 0. So as a consequence of the random variables being uncorrelated, all of the covariance terms go away. And in this case, the variance of the sum is equal to the sum of the variances. One more thing to keep in mind is that if each pair, xi and xj, are pairwise independent, xi and xj are indeed uncorrelated. And then covariance terms are zero, and the variance of the sum is the sum of the variances. This is a funny problem with an interesting answer. So you're at a party and there's n people, at least two, and each person throws a hat into a common box, and the box is shaken, and each person blindly draws a hat from the box. And now we say a match occurs if a person draws his or her own hat. And the question is, how many matches can we expect in executing this silly procedure? What's unclear is whether the number of matches you'll see will go up or down as the size of the party increases. As n gets larger, there'll be more people with a chance to match. On the other hand, as n gets larger, there'll be a reduced probability of matching with your own hat. And so you wonder how will the expected value and the variance of the number of matches grow or possibly shrink with the number of people n. The solution to this problem is surprisingly tricky. You'll need our theorems for the expected value and variance of a sum, but you'll also need to do some pretty careful reasoning about how to calculate the necessary covariance terms. Specifically, what we do is we define xi as an indicator random variable such that it equals 1 if person I matches and 0 otherwise. And because of this, the number of matches out of n people is the number of times person 1 matches plus whether person 2 matches and so on up to person n. What makes this problem interesting is that the xi's aren't independent. They actually have a dependency structure in the following sense. If n equals 2 and the first person matches, x1 equals 1, then x2 also has to equal 1 because the only other hat that will be left for the second person to draw is their own hat. And similarly, if with n equals 2, if the first person doesn't match, then the second person is guaranteed also not to match. So as you increase n, this dependency gets weaker, but it doesn't completely go away. To find the expected value of the number of matches, we know that we can write that the expected value is the sum of the expected values for each user. But now we need to find E of xi for each user I. We can do this by remembering that actually the PMF of xi is kind of simple. Before any hats are drawn, it should be obvious from symmetry that person I is equally likely to draw any hat from the box. So there's a probability 1 over n that person I draws their own hat with probability 1 minus 1 over n, person I draws somebody else's hat, and in that case, xi is equal to 0. So we see that each xi is Bernoulli with success probability p equals 1 over n. And so of course we know that E of xi is also equal to p, which is 1 over n. And finally, the expected number of matches, well, all of the E of xi's are the same. So this will be n times E of xi, which is n times 1 over n equals 1. So on average, no matter how many people, whether it's 2 or 3 or 20 million, the expected number of matches is going to be exactly 1. The variance of Vn is a trickier calculation. we know that we need to use our theorem. It's going to be the sum I equals 1 to n variance of the xi's plus 2 times the sum of I equals 2 to n minus 1 summation j equals 3 to n covariance xi xj. To make the rest of this calculation simpler, we want to use the symmetry in the problem. And the symmetry says that all the xi's are Bernoulli p, so all of the variances are the same. Also, if you think about the problem carefully, you'll realize that, oh, any pair xi, xj, I not equal to j, is equivalent to another, and so all of these covariance terms are the same. So now we can rewrite this as n times the variance of any xi plus 2 times, and there's a factor in the middle here, which is the number of terms in this double sum. So what's happening in this double sum is we're thinking about all ij pairs where I is not equal to j. So from the list of variables x1 through xn, we're picking an xi and we're picking an xj, and they have to be different. And the number of such pairs, if you give it a moment's thought, is n choose 2. And each one of them contributes covariance xi, xj. Since we're running out of space on this slide, let's finish the problem by looking at the solution. To finish the problem, we need to find the variance of the xi's and also the covariance of each xi, xj pair. For the variance of xi, we keep in mind that xi is Bernoulli p, and because xi is Bernoulli p, the variance is p minus p squared, and with p equal to 1 over n. In fact, this is precisely what we obtain over here. For the covariance, things are a little trickier. We know that the covariance of xi, xj is the expected value of xi times xj minus the product of the expected values. The product of the expected values we already know. It's 1 over n times 1 over n. But this expected value of the product, this is also perhaps the trickiest term in the problem. Since xi, xj, they're both binary, the product xi, xj is also binary. It's 0 or 1. And in particular, xi, xj, the product equals 1 if and only if both xi is 1 and xj is 1. Otherwise, the product is equal to 0. It follows then that the expected value is just equal to 1 times the probability that both xi and xj equals 1. So this is also somewhat tricky to find. The way to do it is to calculate the conditional probability that xi is 1 given xj is 1, and then multiply the probability that xj is 1, which is in fact 1 over n. Given xj is 1, that is that the jth person drew his or her own hat, then xi is 1 if and only if the ith person draws his own hat from the other n minus 1 hats. But this probability is exactly 1 over n minus 1 because person I is equally likely to draw any of the n minus 1 other hats remaining in the box, including his own. From this, we can write that the expected value of xi, xj is 1 over n times 1 over n minus 1. It follows from this breakdown into conditional and marginal probabilities. And with this, the covariance of xi and xj is equal to the exi xj term minus the exi times e of xj, and that gives us this expression here for the covariance. Finally, when we put these pieces together, we get that the variance is n times the variance of any xi plus 2 times n choose 2 times the covariance, which is n times n minus 1 times the covariance. And when you plug the expressions we had obtained for the variance and the covariance into this expression, we find out the variance of the number of matches is also 1. Somehow what's happening here is that in terms of expected value and variance, when you grow the size of the party, the probability that you get more matches because you have more people looking is exactly canceled by the probability that the reduced probability of getting your own hat. Here is almost the same problem, but actually it's much simpler. In this case, each person immediately returns to the box the hat that he or she drew. So now each person draws a hat from the full box of all n hats. And whether person I draws their own hat is independent of whether anyone else draws their own hat. So now we define the same xi to indicate whether person I drew their own hat or not. And as before, xi is Bernoulli with success probability p equals 1 over n, the probability that person I draws their own hat. But now the xi's are independent. And the v, which is the total number of matches, which of course is still the sum of the xi's, has very easy expected value and variance to calculate. Particularly, the expected value is n times the expected value of each xi by symmetry, and that's equal to n times 1 over n. The expected number of matches is still 1, but the variance is equal to uh, the sum of the variances. So it's equal to n times the variance of any xi, because there's n of these terms and they're all the same. And if you recall, the variance of xi is equal to p minus p squared. It's equal to 1 over n minus 1 over n squared. And so the variance of Vn is equal to n times 1 over n minus 1 over n squared is equal to 1 minus 1 over n. If you need more practice with this material, take this quiz. It's a lot easier than the first problem with the hats.